There is a chip that is reportedly so expensive to manufacture that it costs nearly as much as a Qualcomm Snapdragon flagship to produce. It is made on a process node that is less efficient, lower yield, and more costly per transistor than the leading-edge nodes available to Huawei's competitors. By every rational economic calculation, it should not exist. No sane company would build it. And yet, Huawei is building it. The Kirin 9100, reportedly a 5 or 6 nanometer processor, featuring Huawei's in-house Maleoon GPU, designed to power the Mate 70 series smartphones. This is the third time in 4 years that Huawei has shipped a chip that was never supposed to exist. First, the Kirin 9000s in 2023, 7 nanometers, made in China, the moment the world realized the sanctions had not killed Huawei's chip division. Then the Kirin 9030 in 2026, 5 nanometers without extreme ultraviolet lithography, proving that multi-patterning could reach nodes the industry dismissed as economically impossible. And now the Kirin 9100, continuing the climb. This is happening right now, today, in 2026. The company that was supposed to be finished is still shipping chips that break the rules of what sanctioned companies are allowed to do. If you want to understand how Huawei keeps doing this, and why they keep doing it even when the economics make no sense, hit subscribe. It genuinely helps this channel bring you more deep dives like this one. Let's get into it. To understand why the Kirin 9100 matters, you need to understand the death sentence that was supposed to end Huawei's chip business. And to be fair to the sanctions architects, the sentence was logical, comprehensive, and brutally well designed. In May of 2020, the United States announced new export controls targeting Huawei. The rules were simple. Any company, anywhere in the world, that used American technology or software to manufacture chips was forbidden from selling those chips to Huawei without a license, and licenses would be denied. This was not a tariff. This was not a trade restriction. This was a kill switch for Huawei's semiconductor supply chain. The logic was clean. Huawei's high silicon division designed world-class chips, the Kirin series for smartphones, the Ascend series for AI accelerators. But high silicon was a fabulous company. They designed chips. They did not manufacture them. Manufacturing required TSMC, the Taiwan Semiconductor Manufacturing Company, the most advanced foundry on Earth. TSMC used American equipment, American software, American technology. Therefore, under the new rules, TSMC could not manufacture chips for Huawei. The last Kirin chip TSMC made for Huawei was the Kirin 9000, released in 2020. After that, the supply was cut off. The official assessment, stated in policy papers and congressional hearings, was straightforward. Without access to advanced manufacturing, Huawei's chip division would wither and die. They would be forced to use older, less capable chips from domestic Chinese foundries. Their smartphones would become uncompetitive. Their market share would collapse. The company would survive, but as a shadow of its former self. And for a while, that looked exactly right. Huawei's smartphone sales plummeted. They lost their position as the #2 smartphone maker globally. They were forced to sell their Honor brand. The narrative was set. Huawei had been contained. This felt like a problem with no real solution. The physics of semiconductor manufacturing require advanced lithography. Advanced lithography requires extreme ultraviolet machines from ASML. ASML machines require Western permission. The kill switch was built into the supply chain itself, until Huawei decided that the supply chain was not the only path to a chip. So here is the question everyone asked, and it was a fair question. If Huawei was cut off from TSMC, why did not they just use domestic Chinese foundries? Why did it take 3 years for the Kirin 9000s to appear? And why is the Kirin 9100 still struggling with yield and cost issues? The answer is that domestic Chinese foundries were not ready, and the reasons they were not ready are specific, brutal, and instructive. The most advanced Chinese foundry is SMAT's, Semiconductor Manufacturing International Corporation. In 2020, when the sanctions hit, SMIC's most advanced process node was 14 nanometers. That is 3 generations behind TSMC's leading edge. 14 nanometers is fine for mid-range smartphones. It is not competitive with flagship processors. To reach 7 nanometers and below, you need extreme ultraviolet lithography, EUV, and EUV machines are made by one company, ASML, in the Netherlands. ASML cannot sell EUV machines to China due to export controls. Therefore, SMS could not reach 7 nanometers. The physics forbade it, or so the consensus said. But there was a theoretical alternative. It is called multi-patterning with deep ultraviolet lithography, DUV, the older technology. Instead of using one exposure of EUV light to print a feature, you use multiple exposures of DUV light, carefully aligned, to build up the same feature. It is like drawing a thin line with a thick marker. You cannot do it in one stroke, but you can do it by drawing two thick lines that overlap in just the right way. The physics works. Multi-patterning DUV can theoretically reach 7 nanometers, maybe even 5 nanometers. But the industry dismissed it as economically insane. Let me explain why, with 3 specific problems. Problem 1. Cost. Every additional patterning step doubles the cost of that layer. To reach 7 nanometers with DUV, you need triple or quadruple patterning for the most critical layers. That means 3 or 4 times the cost, 3 or 4 times the time on the lithography tool. The cost per chip skyrockets. Problem 2. Yield. Every time you expose the wafer, you introduce the possibility of misalignment. If your second exposure is off by even a few nanometers from the first, the features do not line up correctly. The chip is defective. With multiple patterning steps, the probability of misalignment compounds. Your yield, the percentage of chips that actually work, drops dramatically. Problem 3. Throughput. Lithography machines are the bottleneck of any fab. If you quadruple the number of exposures, you quadruple the time each wafer spends in the lithography tool. Your throughput collapses. You need 4 times as many machines to produce the same number of chips. Because of these 3 problems, the industry consensus was absolute. Multi-patterning to 7 nanometers and below is physically possible, but economically suicidal. The cost per chip would be astronomical. The yield would be terrible. The throughput would be glacial. No rational company would ever do it. The dismissive nickname in the industry was the poor man's EUV, a technique that technically works, but only a desperate company with no other options would ever attempt. That assessment held for 3 years, right up until a desperate company with no other options decided that economic suicide was better than technological death. Here is the twist, and this is the part that changes everything. Huawei and SMIC did not try to make multi-patterning economically competitive with EUV. They could not. The math does not work. Instead, they reframed the entire problem. They stopped asking, how do we make this cheap? And started asking, how do we make this work at all? And the answer was, accept the cost, accept the yield hit, accept the throughput penalty, and then optimize everything else in the process to compensate. Let me walk through the mechanism, step by step, of how this played out across 3 chip generations. Generation 1. Kirin 9000s, released in August 2023, inside the Huawei Mate 60 Pro. This was the shock. The world expected Huawei to be using 14 nanometer chips. Instead, they shipped a 7 nanometer processor, manufactured by CIMIC, on Chinese soil, without EUV. The Kirin 9000s was not competitive with Apple's A17 Pro or Qualcomm's Snapdragon 8 Gen 3. It was slower. It was less power efficient. But it worked. It was a real, functional 7 nanometer chip. And it proved that the poor man's EUV approach was not just theoretical. It was real. Generation 2. Kirin 9030. Released in 2026, inside the Huawei Mate 80 series. This time, 5 nanometers. Again, manufactured by CIMIC. Again, without EUV. Again, using multi-patterning DUV. The Kirin 9030 is a more ambitious chip. 9 CPU cores, 1 supercore running at 2.75 GHz, 4 large cores at 2.27 GHz, 4 efficiency cores at 1.72 GHz. It scores 1,131 in Geekbench single-core tests, 4,277 in multi-core. That is a 76% performance improvement over the previous Kirin 9020. And it achieved this on a 5 nanometer node that was built with nothing but deep ultraviolet tools. Generation 3. Kirin 9100. This is the chip we are here to talk about. Reportedly 5 or 6 nanometers, featuring Huawei's in-house Maleoon 9110 GPU, designed to power the Mate 70 series. Let me walk through the mechanism of how SMIC makes these chips work, step by step. Step 1. Selective multi-patterning. Not every layer of a chip requires the most advanced resolution. The critical layers, the metal interconnects, the transistor gates, need the finest features. The non-critical layers, the power distribution, the bulk silicon, can use standard single patterning. SMIC optimized their process to use quadruple patterning only where absolutely necessary, and single or double patterning everywhere else. This cuts the average cost increase from 4 times to roughly 2 times. Step 2. Advanced alignment systems. To solve the yield problem, CIMIC invested heavily in overlay accuracy. They developed proprietary alignment algorithms and upgraded their DUV machines with enhanced metrology systems that can detect and correct misalignment in real time between each exposure step. The result: overlay accuracy good enough to maintain yield even with multiple patterning steps. Step 3. Design optimization. Huawei and CIMIC worked together to design the Kirin chip specifically for the constraints of multi-patterning DUV. They avoided certain layout patterns that are particularly difficult to print with multiple exposures. They optimized the transistor density to balance performance with manufacturability. They made design sacrifices that a company with EUV access would never need to make. Step 4. Process integration. This is where the real engineering lives. CIMIC developed proprietary etching and deposition techniques that work synergistically with multi-patterning. After each exposure step, they use advanced etching to sharpen the features, removing the roughness that multiple exposures can introduce. They use atomic layer deposition to fill gaps with perfect precision. The entire process flow is optimized as a system, not as individual steps. And here is the brilliant part: the 3 killers of multi-patterning: cost, yield, throughput. They do not get fixed. They get accepted as the price of independence. The chip costs more to make than it would with EUV. The yield is lower than TSMC's EUV process. The throughput is slower, but the chip exists. It works. It ships. That is not a metaphor. That is just the engineering, and it is why the Kirin 9100 is real, even though the economics make no sense. But benchmark numbers are one thing. A phone on sale is another. And this is where the story stops being a technical achievement and becomes a commercial reality. The Kirin 9000s shipped in August 2023, inside the Huawei Mate 60 Pro. The phone sold millions of units in China. Consumers bought it not because it was a patriotic duty, but because it was a good phone with a good chip. The Kirin 9000s delivered flagship-adjacent performance. The phone had a great camera, a beautiful display, fast charging, and all the features consumers expect. The fact that it was built without EUV lithography was a technical detail that most buyers never knew or cared about. The Kirin 9030 shipped in 2026, inside the Mate 80 series. Again, millions of units. Again, competitive performance. Again, the chip works. Now let us look at the Kirin 9100. This chip is reportedly powering the Mate 70 series, specifically the premium models, the Pro, Pro Plus, and RS Ultimate editions. According to reports, only the high-end models receive the Kirin 9100, while the base Mate 70 uses a less advanced chip. This is a strategic decision. Reserve the most expensive, lowest yield chip for the models that can absorb the cost premium. And the cost premium is real. Reports suggest that the Kirin 9100 is nearly as expensive to produce as Qualcomm's Snapdragon 8 Gen 3. That is staggering. The Snapdragon 8 Gen 3 is manufactured on TSMC's 4nm node, with EUV lithography, with high yield, with massive throughput. The Kirin 9100 is manufactured on CIMIC's multi-patterning DUV process, with lower yield, with slower throughput. And yet the cost is similar. How is that possible? The answer is that Huawei is absorbing the cost penalty. They are not passing the full cost on to consumers. They are subsidizing the chip to keep the phone price competitive. This is not a profit-maximizing strategy. This is a strategic imperative. Now let us look at the manufacturing scale. SMIC is ramping production of these advanced nodes. Industry reports suggest SMIC is targeting 100,000 wafers per month of leading-edge output, 7nm and 5nm combined, by 2028. That is a 5-fold increase from current levels. To put that in perspective, 100,000 wafers per month, with roughly 500 chips per wafer, is 50 million chips per month. That is 600 million chips per year. That is enough to supply every smartphone Huawei sells in China, with capacity left over for other products. And the investment backing this is enormous. SMIC has built new production lines in Shanghai specifically for advanced node manufacturing. The capital expenditure is in the billions of dollars. This is not a research project. This is an industrial commitment. Now zoom out to the national policy layer. The Chinese government has made semiconductor self-sufficiency a top strategic priority. The National Integrated Circuit Industry Investment Fund, the so-called Big Fund, has deployed over 300 billion yuan across 3 phases. Phase 3 alone is targeting advanced nodes, including 5 nanometer and beyond. The message is clear. The cost penalty of multi-patterning is acceptable. The yield hit is acceptable. The throughput reduction is acceptable. Because the alternative, permanent dependence on foreign technology, is not acceptable. This is happening right now, today, in 2026. The kill switch was flipped, and the machine kept running. But here is the honest part of this story, and I want to be straight with you, because this format does not do blind hype. The Kirin 9100 is a remarkable achievement, but it is not equivalent to what TSMC is shipping with EUV, and pretending otherwise would undermine the real accomplishment. First, the cost. Multi-patterning DUV is significantly more expensive per chip than EUV lithography. Industry estimates suggest the cost premium is roughly 2 to 3 times. That means every Kirin 9100 costs substantially more to manufacture than an equivalent chip would cost TSMC. Huawei is absorbing that cost, subsidizing the chip to keep phone prices competitive. But that is not a sustainable long-term strategy. Eventually, the economics have to work. Second, the yield. Even with advanced alignment systems, multi-patterning has lower yield than single-exposure EUV. More chips come off the line defective. That means more wasted wafers, more wasted materials, more wasted time. The yield gap is probably 10 to 20 percentage points behind TSMC's EUV process. Third, the performance ceiling. The Kirin 9100 competes with current flagship chips, but it is not leading the industry. Apple's A-series chips, manufactured on TSMC's most advanced EUV nodes, still have a performance advantage. The gap is smaller than it was, but it is not zero. Fourth, the roadmap limit. Multi-patterning DUV can reach 5 nanometers, maybe 3 nanometers with extreme effort. But beyond that, the physics really does become impossible. The number of patterning steps required becomes so large that the cost and yield problems become insurmountable. At some point, probably around 2 nanometers, China will need EUV or an equivalent breakthrough, or they will hit a hard wall. None of this erases what the engineering has already proven. It simply marks the distance between a working solution and an optimal solution. The chip works, the chip ships, the chip competes. The rest is economics, yield, and the long-term roadmap, which brings us back to the bigger picture this whole story has been building toward. Because this is not really about one chip. It is about what happens when you try to use supply chain control as a weapon, and the target refuses to play by your rules. The sanctions against Huawei were built on a simple premise. Advanced semiconductors require EUV lithography. EUV lithography requires ASML. ASML requires Western permission. Cut off the permission, and the capability disappears. It was elegant. It was logical. It was backed by the best technical minds in Washington. And it failed. Not because the physics was wrong. The physics was right. EUV really is the optimal path to 5 nanometers. Multi-patterning DUV really is more expensive, lower yield, and slower. The sanctions architects were correct about all of that. What they got wrong was the assumption that economic optimality is the only path to capability. They assumed that because multi-patterning is suboptimal, no rational actor would pursue it. They did not account for the possibility that a company, backed by a government that views technological independence as an existential priority, would accept suboptimal economics in exchange for strategic autonomy. And now look at the result. Huawei has shipped 3 generations of advanced chips. The Kirin 9000s, the Kirin 930, the Kirin 9100, all manufactured in China, all without EUV, all working at scale. The world that ran on EUV lithography did not announce its own ending. It just started losing its monopoly to someone willing to take the expensive, inefficient, suboptimal path to the same destination. So here is the question I want to leave you with, and I genuinely want your answer in the comments. When a technology embargo fails because the target accepts economic pain in exchange for strategic independence, what does that tell us about the future of technology sanctions? Are they still effective tools of statecraft? Or have we entered an era where any sufficiently motivated country can find a workaround, no matter how expensive? Drop your answer below. I read every single one. And if you want to be here for the next time an impossible chip goes on sale, hit subscribe. We are building something here, and the next few years are going to be the most consequential decade in the history of semiconductors. You are going to want a front row seat. I will see you in the next one.